Hi, welcome to the notes for graphing exponential functions. And before you take these notes, make sure that you completed the math lab on Schoology for discovering the parent graphs of exponential functions and their transformations. So the front and back cover of the notes booklet for this lesson is to summarize what we learned in that math lab on Schoology. So we'll begin with the definition of an exponential function. Exponential functions have a variable in the exponent. So y equals b to the x is exponential given a value of b that is greater than 0. Okay, exponential growth occurs when that value of b, the base of the exponential, is greater than 1. And that would be a rate of change that is increasing. So as you look on the back at this parent graph for a base greater than 1, you'll notice it starts out with a very slow rate of change. The slope is almost horizontal along that asymptote, and then as it bends into that J-curve shape, you see the slope is getting steeper, steeper, steeper very quickly. That would be an increasing slope or increasing rate of change. Exponential decay, on the other hand, occurs when the b, the base of the function, is between 0 and 1, non-inclusive. And when you look at that parent graph for exponential decay on the back of the notes booklet, you'll see that the slope starts out very, very steep, and then it gets shallower and shallower, less steep and less steep as the function approaches that horizontal asymptote along the x-axis. Okay, then we'll notice on the back where we compare and contrast the exponential growth and decay parent functions that both functions always will pass through these same three anchor points. 0, 1 will always be the y-intercept, and then the point 1 comma b, and -1 comma the reciprocal of b. Those are your three anchor points regardless of whether it's exponential growth or decay in your parent graph. Okay, then the horizontal asymptote is located along the x-axis. That's the equation y equals 0. The domain for every exponential function is all real numbers, so the open interval -infinity to +infinity. The range of the parent graph is 0 to infinity. All of your values are going to be above the x-axis for the exponential growth and decay parent graphs. So next we're going to take a look in the notes at transformations of exponential functions. And this list of transformations is exactly the same as what we did with our other parent graphs. Remember, we did quadratic and cubic, rational, ceiling, floor, all of those square root and cube root, all those parent graphs excuse me, had the same sort of transformations where k was a vertical translation up if it was positive or down if the k was negative. Right? In all of our parent graphs, h controlled the horizontal translation. If you had an x minus h, so your h is positive, it would shift the graph to the right. If in the parentheses you see x plus h, recall that's a negative h, x minus a negative h makes a positive, that would shift the graph to the left. Okay, a greater than 0 is a reflection, or I'm sorry, a less than 0 is a reflection in the x-axis. So when your a is negative, your graph flips over the x-axis with a vertical reflection. When your a in absolute value is greater than 1, that's going to be a vertical stretch. And when the absolute value of a is less than 1, that will be a vertical shrink. In our previous parent graphs, when we did transformations earlier in the year, we also had another variable here in front of the x, and that was a c, where we would use that to identify horizontal stretch and shrink and reflections in the y-axis. That still is the case. It will excuse me, still be there, and you can control the transformations with respect to the horizontal stretch and shrink and y-axis reflection using that value. But just to make things a little more simple, excuse me, in the notes, we're going to exclude looking at that particular feature for these problems that we're going to go over together today. Okay, then since this is an exponential function, we use the variable b to represent the base of the exponential. So b is the base. When the b is greater than 1, that's exponential growth. When the b is between 0 and 1, non-inclusive, that is exponential decay. We use that b to identify the guide points on the graph, the parent graph. So 0, 1, that's our y-intercept, 1 comma b, and negative 1 comma the reciprocal of b. And we can also, without looking at the graph, just having the equation in front of us, we can determine the equation of the horizontal asymptote. That's going to be the line y equals k. The domain of all exponential functions is all real numbers. And the range is going to be determined not just by the location of that horizontal asymptote, but also we have to consider if there's been a reflection in the x-axis, because that will change our range. So if there is no reflection in the x-axis, if the a is positive, then the range is going from that horizontal asymptote up to positive infinity. If there has been a reflection and the a is negative, then the whole graph flips upside down and our range becomes negative infinity up to, but not including that horizontal asymptote of k. So we're going to use these transformations in order to quickly match the graph of these functions to the equation that goes with it. So looking at number 1, y equals 5 to the x, that's going to be the parent graph of an exponential growth function. And we know that those functions always pass through the y-intercept 0, 1 and have a horizontal asymptote along the x-axis. So when we look at those options for the graph, we've got only one that meets that criteria, and that would be graph B. So the answer to number 1 is going to be B. Right, and we know that because it goes through the y-intercept 0, 1 and has its horizontal asymptote along the x-axis. Okay, then looking at number 2, we have y equals 5 raised to the quantity x plus 1. That is going to shift to the left 1 unit. So the asymptote has not changed, but instead of the function passing through 0, 1, if I shift everything to the left, it's going to pass through negative 1, comma 1. So as I look for that graph, here's one where the horizontal asymptote has stayed the same as the parent graph, but I notice that instead of passing through 0, comma 1, now the equation is at negative 1, comma 1, because that's a shift to the left of 1 unit. So that would be graph D. Okay, now looking at number 3, y equals negative 5 to the x minus 1. Okay, this negative out front makes reflection in the x-axis, so the parent graph has flipped upside down. But then the k being negative 1 also translates the graph down 1 unit. So we need the function that has its horizontal asymptote now at negative 1. And when we look at all of those choices, the only one that has its asymptote at negative 1 is C. And so that is going to be graph C for number 3. Okay, then in number 4, Same reflection in the x-axis with that negative a, but then instead of going down 1, this is our h of 1, so we head to the right 1. So the horizontal asymptote is still in the same place at 0, but the graph has been reflected over the x-axis and translated to the right 1 unit. So when we look at a graph that meets those criteria, here in A, right, there's our horizontal asymptote along the x-axis, but instead of the function passing through 0, if we reflected it, it would be 0, -1, it shifted 1 to the right, and it's at +1, comma, -1. And so graph A would correspond to number 4. Okay, then in number 5, since the negative is up here with the variable, that would be a reflection in the y-axis, so side to side, or you can, probably easier way to even recognize that is, remember, a negative exponent means to take the reciprocal of the base. So that would be equivalent to 1/5 to the x power plus 1, and 1/5, instead of being exponential growth, is exponential decay. So this graph needs to start steep and then start to flatten out as it heads to the right. So when we look at the graphs that do that, that start steep and then flatten out, we also want to keep an eye on this +1, which moved everything up 1 unit, and that would be graph F. Right? We can see here our asymptote is up 1 unit, it starts out steep, and then it flattens out. And so number 5 corresponds to graph F. And then number 6, y equals -5 to the negative x. This is going to be the same as -1/5 raised to the positive x, because again, that negative exponent means to take the reciprocal of the base. So we have a horizontal asymptote along the x-axis, a reflection in the x-axis, so it's flipped upside down, and it's an exponential decay function, so it starts out steep and gets shallow. And so we can see here in graph E, this slope starts steep, it gets flatter, flatter, flatter as we head off to the right, and that would make E our graph number 6. Okay, now example 1 in the notes, we want to write the equation when the parent function of 7 to the x has been reflected in the x-axis. So we know that we're starting out with a negative in the front, right? Reflected in the x-axis means the a is negative. Okay, it needs to be translated 5 units to the left. And so I know that my exponent is going to be an x plus 5 because I'm going 5 units to the left. It needs to be translated up 2 units. So that's going to be my k. So k is equal to 2. My h, since it went to the left, forgot to write that in there, was -5. So we're going to go up 2. At the end for the k, and it's been vertically stretched by a factor of 3, and so that tells me that the absolute value of a is equal to 3. Now I know from the reflection that my a had to be negative, so now I know that because of that vertical stretch, my a has to be a -3. And so I have -3 times 7 raised to the quantity x plus 5 and then plus 2. Okay, the domain is always all real numbers, so the interval -infinity to +infinity for an exponential function. The horizontal asymptote is the k, So y equals 2 would be the equation of the horizontal asymptote. And then the range. So since there has been a reflection in the x-axis and my k is equal to 2, I know that my range is negative infinity to 2 non-inclusive.